clinical and biological informatics. So today, my focus will be more like ontology and adverse events and the different applications. So these are the keywords of my talk. So first, I will introduce, I will have some quick introduction on the background of adverse event and ontology and other conventional tools. And then I will introduce the OAE and then the OVAE, the focus on vaccine. And then I will demonstrate that it's not only for vaccine, it can also be used for drug study. We can develop class level ontologies to study drugs. So this tool can be used as more like we call the knowledge base, ontology-based knowledge base. So the OAE is more for the terminology for the ontology-based classification of different adverse events. This can be used as knowledge base. And I'm going to switch the gear a little bit to introduce some basic molecular level studies and using the interaction network ontology. And then I'm going to quickly introduce some tools our group has developed. So first, I think I don't have to talk too much in this audience. We all know the adverse drug reactions is a very important domain, and it's the fourth leading cause of death ahead of many famous ones like AIDS and pneumonia. So how USA monitors adverse events? Basically, there are two services. One is called FAERS. So previously it's called AERS. There's no F, and later they put F there. So it's a vaccine, so, FDA adverse event reporting system. And another system is called VAERS. So VAERS is for vaccine case report. So there are two different systems. So this one is more FDA, this one is more CDC, but FDA is also part of the collaboration. So the adverse event representation systems including many, like COSTAR. And COSTAR is quite an old one, and then later on COSTAR merged into MEDRA. So MEDRA is a medical dictionary for regulatory activities. So this is more like the de facto system for the both FAERS and VAERS system. And for NCI, if it's a drug for cancer therapy, then NCI will require you to use the CT-CAE system. So this one is for the common terminology criteria for adverse events. So one uniqueness of this system is like they put every adverse event into different grades. So they have from grade 0 to grade 5. So grade 5 means death, so always is death. Grade 0 is so it's more like a gradual increase of severity. And then for WHO, they have WHO Art. This one is relatively simpler compared to the measure. And many countries, and as I know, including China, they are using WHO version. They're not using measure version. So all those we consider they are all controlled terminologies, and we think they are not ontology. So I'm going to tell you what is ontology. Well, you all, I think most of you know. But anyway, let's come to some story. So if we want to see ontology data, why measure is not good? Well, it's before the one. So measure has 5 layers. So they have the top layer is called SOC, the system organ level. And then they have high level group term, high level term, preferred term, and the low level terms. So low level terms can be many terms which probably are synonyms to the preferred term. So what's the problem with the measure? As I think, and many things too. So they don't have definitions. They do have coding. So every term they have a specific code, a digital code. Then the pin has the ID. But they don't have definition. So sometimes we are talking about a fever, for example. We don't know what's called a fever. And the 5 layers are often arbitrary because sometimes using the I do need 6 layers. Sometimes you think, oh, 3 layers is enough. So they always put it into 5-layer certain, so it's very quite arbitrary. And the synonyms are often not synonyms. Well, sometimes they say, okay, swollen eyelid and swollen eyes, they are synonyms, but of course you know they are not synonyms. So one is eyelid, one is eye. And duplicated classes, so like eye swollen is a subset of eyes swollen. Doesn't make sense, right? They are the same thing. And it's hierarchical confusion. So for example, this one I copied from the major certain from the NCBO Bioportal. So you can see like, okay, we have acute and chronic thyroiditis. This is subclass level, and then they have something called thyroiditis. So this one, you would think this is more like a parent term of this one, right? But even for this, you don't know. Probably it's very hard to find any thyroiditis which is acute and at the same time is chronic. They are opposite one. And now you put that together, the term itself has some issue. And now you have the thyroiditis acute and the chronic. This should be the subset, the subclasses of the thyroiditis, but they all put it all together. So you can see these kind of things, they occur a lot. So it does have some issue, and it's quite old. And even in addition, and you have to buy a license. For USA, it's no problem. But if you want to use it for commercial purpose, you may have to pay license, and for many other countries, you cannot use it. So many issues. So let's see, what is ontology? So the CTSA definition is a representation of entities and relations in a part of reality in computer and human interpretable forms. So computer can do it, and a human can read. So like, for example, we have some form like this one. So it's a selective serotonin reuptake inhibitor drugs. So you have many, they are the drugs, and the drug has a role of antidepressant drug role. And then this is instance level, and this is class level, instance level, so different persons may be described with the drug, and for each person you may have some quality. So you basically organize those things in a very clear way, and we can do all kind of query over the system. So yeah, so basically they are more or less like 2 schools in ontology development. So I think currently the so-called OBO system has gained its popularity. So OBO means open biological and biomedical ontologies. So there are some principles. So my favorite one is open. You don't charge anything, even for commercial development. You don't charge for. You don't say, okay, you have to pay me. You don't do it, and it's collaboration. So we enjoy all the people, if we have the same interest, just come to do it together. Okay, so this is some background. So let me come to the OAE development. So the OAE was initially developed by my group. Initially, it was more like a branch of the vaccine ontology. It's our focus on representing the vaccine adverse events, and later we put it out, and now becomes more like popular beyond vaccine, because drugs or even others like a medical device, surgery, they all have adverse events. So we can use a single certain to represent them. And we does not assume AE causality. So you have AE, you don't say, okay, this one has to be due to some medical intervention. So it follows with the VAERS and FAERS definitions. So it's likely, the main thing is like it's caused by, or it's occurs after. So let me come to this example. So this is the two, even just the 2 simple terms we argued for years. So eventually we come to this one. So for the adverse event, it's preceded by medical intervention. It may be or maybe not due to the medical intervention. So the causality is not assumed. So for the causal adverse event, so it's induced by, everything the same, this is induced by, this is a subset of preceded by, so it means it's causal. So we classify them in 2 different ways. to support our later study. So you can generate some models, like this one. You can see, okay, this is where it occurs, yes, we have the patient as participant of the medical intervention. The patient may have adverse event in different locations. So you basically, you have a certain that aligns with all the pieces all together. It's not like a magic. It's basically just symptoms. But for our case, we more consider it's a pathological process. It has time and it has those relations with the patient, with the anatomical entities. So all linked together is very good, strong, solid pattern system. So we can study more on the reasoning. So currently, we have many turns, over 4,000 turns, and more than half is OAE specific. So that means it is adverse events. We do have many turns from Uberon, for example. So they are the anatomical locations. So we specify, okay, this like eyelid swollen, so it occurs at the eyelid. So you can look for the locations. So it across to different sections. So we input all those. While you think, oh, this is so difficult to do. Why bother you do all those kind of things? Well, we think it supports the ontology interoperability, and we do have tools. Actually, you can do it quite easily. And so the whole screenshot is coming from the Ontology, and how to get all the turns to OAE. We have other tools like something we call the Ontofocus, and I'm going to introduce briefly later. So we have our ways to assess causality, because causality is a bigger issue. The main idea is like, okay, a patient gets some adverse event after some drug or some vaccination. So the question is like, is the adverse event, or especially if it's a severe adverse event, is due to the vaccination or due to the drug administration? That is the central question. So we are starting to put some like methods or some ways into the ontology, so we can support the future automated analysis of the story. And here I want to represent one case which was published 3 years ago, how we can use OAE and how it can compare with the measure. So the case is to look for the killed inactivated versus live influenza vaccines. So if I ask you which one is safer, so you have two options. So you are worried about adverse events. Which one you would choose? So the majority will choose the live one, so no killed one. This killed is safer. However, our study shows the live one may be safer if we are talking about severe adverse events. So basically, this is the method that we do. So we look for the VAES data, and all the data is mapped to measure. We don't have OAE, so of course we have to use measure. So measure vaccine peer extraction, and you can do traditional methods like a PR, chi-square, or minimum case filtering, and then we can have enriched AEs. And then because we don't trust measures hierarchy, so we use our OAE hierarchy. So this is the key, where OAE can be used, and then we can look for the classification. So the classification actually becomes very important for us. So for the TIV and or live, the killed one or live one, we just do it 2 times and we compare. So what we get is like this way. It's a summary of some results. So what we find is the killed influenza vaccines, they are more associated with neuron adverse events. So you can see, like for example, this is a killed one. They have muscular one, and the neuron certain have 5. This is 1, and this is so it's muscular. So killed one is more injection. So have muscular and also have more neuron side, and the live one is more like a respiratory. So you have to like do the spring, so you can get it vaccinated. So it's no wonder you have some respiratory. But those are quick, they are mild. So we found actually this is the respiratory one. So live one is more. So if you look for the severe adverse events, the killed one actually is significantly statistically enriched, the Guillain-Barré syndrome or the paralysis. But for the live one, it's not significantly enriched. So we found it's fourfold. So if you use the killed one, let's say if 1 out of 1 million, you may get the parentheses. So for the live one, maybe the killed one is 4 out of 1 million. So it's actually it's more severe to get it. And you will think that the paralysis is more similar to the other neuron or muscular certain. So you classify them, it's likely there's a transition, right? So many people get the neuron adverse event, but only some small people they advance to the severe adverse event, which is also neuron type. So you do the clustering, which help you to understand the whole certain. So I think it's one advantage. So what about, if I use other certain? So we did compare OAE with Major, with SNOMED, which is another popular certain. Well, definitely OAE is simpler. And yeah, we don't have time to go for detail. If you go for detail, you will see, okay, definitely OAE makes more sense. And we did have a very thorough discussion in our paper. So this is one use case to show OAE really can be very good. So now I want to change the story a little bit to the two other stories. So basically, OAE as a whole is to classify adverse events, but we can use it with other information to form a knowledge base of some specific stories by extending OAE with the other ontologies, like with the vaccine ontology. So we can come to the OVAE. So vaccine ontology, we initiated the work many years ago. So it also like OAE is following the overfounding principles. It's aligned with the basic formal ontology. So I can give you one example. So this is the basic formal ontology. So you will say, okay, everything is in the whole world is more like you will think it's 4D, right? So it's 3D space or site plus the time process. So this is continuum is associated with time. So anything associated with time is continuum. So anything associated with 3D is another story. So basically, buffer has 2 branches. So we treat anything associated with space is continuum. Anything associated with time is occurrent. So we think a vaccine is a process material, and which is a material entity which is independent continuum. So independent means it can state itself. But if you think a color cannot state itself. It's dependent continuum. So it's just some quick introduction of the buffer, which has been used by more than 100 biomedical ontologies. So it's very quite popular. So we can classify those things in this way. Like I use one example, some influenza vaccine. And so this vaccine is an influenza vaccine. It has this hierarchy. And we can generate many attributes associated with the influenza. So you can see, it's distributed by the company, manufactured by the company, and it has some phenotype. So it's a way that a machine can read. So let's think about OVAE. So this simple paragraph, maybe you are familiar. It's not only for vaccine, but for any drug. You may see an instruction, right? You open the capsule, you can see some instruction. So the instruction can be like this one. So for this alpha-rare, you will see 5 to 7 years of age. There are some injection site adverse event like pain, redness, swollen. They have different percentage for different age. So this information is good. Of course, you can use little money to find it out, but it may not be accurate. And also, how can you compare with all those kind of adverse events among different vaccines? So, well, our approach is to develop so-called OVAE, so it's a vaccine ontology of vaccine adverse events. The whole idea is to make it as a knowledge base. So let's say if we have this paragraph, you get it from FDA package insert, right? So you can represent it in the ontological way. You say, okay, I have 5 to 17 years old, I have pain, and then the occurrence is 60% or over 30%. So you can do all those kind of things. You can present them in an ontology. Of course, you will think it's quite time-consuming. but just remember, you do it once, right? You do it once, and it will be available forever. So we did with all the vaccines using this strategy, and then we can do a lot of analysis, and we can get a lot of insights. So we can just make some very quick queries, just a few lines of Sparkle probably, and then you can know, okay, what's the top 10 vaccines with the largest variety of adverse events. Like, oh, I find that there's something like Combivax HB, hepatitis B, oh, it has 20 adverse events. So some has less. So you can ask another question, what adverse events are most frequently reported? So you do another very simple query. You know that, oh, pain, yeah, pain is like, we have about 70% of time you do any vaccination, you may get a pain. So this is kind of something, once you build up an ontology-based knowledge base, and you can use it, it's not read on your local database. You can do anywhere, and it's open, and you can use it. So it's one demonstration how ontology can support a knowledge base, support looking for insights of adverse events. So just give you another example. It's a similar idea, but now it comes to drug. So this one is a collaboration with FDA. Yeah, sorry, I didn't put a disclaimer. I gave another talk just for this one. I put a disclaimer because we have a collaborator from FDA. So this idea is like to look for the drug neuropathy. So many drugs can induce neuropathy problem, and some drugs like whatever, can induce the neuropathy problem in a large population, right? So you do want to find what's going on there, find some story, mechanism, and see how you can deal with it. So we use the different ways to try to get an inclusive list of drugs that can induce neuropathy. So we did visual mining. We use some Mayo Clinic ADpedia, and we use the University of Pittsburgh, the linked SPLS. So we look all of them. Eventually, we find 215 drugs. They are one way or the other associated with neuropathy. So how do you deal with it, right? So it's the idea, can you represent them using more like an OVA kind of thing? And why bother? Why do it? It's quite simple. Why do it? Can you get any benefit? Can you look for any insights out of the story? So, we are thinking, we should be able to do something. So we can, for the adverse events, we can use OAE. If it's a drug, we can use some like drug ontology or some other options. We use drug ontology. If it's chemical, so each drug is associated with a chemical compound. So we use CABI to represent the chemical information. And if we are looking for the roles or the mechanisms of the drug, we use NDFRT. And if it's a biological process, we use gene ontology. So now our task is to use all those kind of things to represent the different aspects of those drugs so they can induce neuropathy. So this is our hierarchy. We use buffer, and if it's material, we go to this side. If it's occurrent, associated with time, go to this side. This is a 3D site or material. This is a time process. And and we also use different things to represent the different stories. And we have a design pattern. We design a pattern like you have a drug, and the drug has some chemical elements, and the drug has some role, and we use NDFRT, and the drug is a drug product, and so for the patient you get the drug administration, and it's a human here, so the drug may do something in the body, and it's realized in human, and the human has a quality, so that means like now age can associate with the neuropathy, so you can link all those things later. Also, we didn't do it later on. We can see, okay, how age can link to adverse events, so because you have all the patterns over there, and this is an example, and we use the Prion structure, so we can represent all these things like very nicely and in a very quite concise and simple way. Then again, let's see, whiteboarder, right? So we look for all the adverse events, and we find all the drugs. There are so many drugs. They are inducing different type of adverse events. So we put them in the structure of OAE. And we can look for this is NDFRT, sorry, right? Look for the roles. And actually, very interesting. You find a lot of agonists and antagonists, and they actually for the same compound. They occur at the same time. So it seems like two more or two less, not good. They always inducing some kind of neuropathy, and you can find a lot of patterns here. You can find many patterns here. So it's a very interesting story. And what about the compound? What about the chemicals? So after you put all the things in a nice structure, you can classify them. This is CADI. So all the terms are associated with the neuropathy. So you can find, okay, this is actually the entity with the most drugs inducing neuropathy. So you can even go further. You can find, under this one, there is one heteroorganic entity, and you can go further. So our FDA collaborator, Dr. Yongqun, liked this one very much. And he thought, oh, this is wonderful. Maybe we should do something more, like maybe look for the chemical structure and trying to find something common. So basically, this is just a simple organizing the structure. And then you can do more. You can do the heat mapping. You can probably find more information, more correlation between compounds and the different type of neuropathy. So really, so the whole thing is to demonstrate, and you can do the query, to demonstrate that just if you can organize your drugs in a nice way by cross-reacting, cross-using different ontologies, stories are built already in the ontology. You just analyze the ontology, don't analyze anything else. So it's very good, a simple demonstration how powerful it can be, and it can be reused by other computer systems. So this is yet another story. So I just want to convince you that the simple ontology development can provide a knowledge base, and the analysis of the knowledge base can give you some insights about the whole system, about the drug neuropathy in this case. So next, I'm going to more like a basic one, more like a gene-to-gene interaction story. So, so I still use the vaccine as an example. So first, I will see the vaccine ontology can support virtual mining. This is our whole pipeline. So for example, initially we use all PubMed abstracts. And we can, so if we have a question, we are looking for interferon gamma and vaccine-associated gene-to-gene interaction network. And we can split the sentences, and we can tag the sentences for the names of genes or proteins and vaccines. And we can filter out some things that we don't want. And then we can find if they are interacting with each other. So to find if they are interacting, so initially we use the over 800 keywords. So basically, it's like interact or interacted, bind, bound. If you find any of the keyword, it means the sentence is talking about some interaction. So we require this kind of keyword in the sentence to show it is really doing some interaction thing. So we do some centrality analysis and do some more further analysis. This is our pipeline. So here I want to emphasize one thing is the I know. So we did this. I think many people do it. So we did 800 keywords, and this is just the indication is interaction. But we didn't know if we just use the keywords, you didn't know what type of interaction. The interaction actually is like a OAE. It has its own hierarchy. So interaction itself may have some internal relations among different interactions. So this is something I want to do. I want to talk more later. And we do have something called ontology of genes and genomes, and now it's getting its popularity now. Many people are using it. So this is different from gene ontology. So gene ontology is about gene products, three things, right? Like molecular function, biological process, and cellular components. So none of them is about the gene itself. So we have the ontology of genes and genomes, and it's really about the genes. We list for every single gene in the genome, we have our own ontology IDs. And currently, Mayo Clinic is using our OGG. We're collaborating and trying to use OGG for the human genetic evaluation story. So this one is to show we can use the ontology to support the analysis of the interferon gamma vaccine interaction network. Again here, so the ontology can, let's say for example, you have a sentence which is talking about a BCG, but there's no sign of any vaccine there in the sentence, right? But so you don't know, the program doesn't know it's a vaccine-associated sentence. But the ontology knows, it is BCG is a tuberculosis vaccine. So by using the simple hierarchy, then you can get more genes identified. And so if you're looking for, this is more adverse event associated. We are also looking for fever. So if you are looking for the fever network with the vaccine ontology, then you can know more papers talking about the vaccine-associated fever. So it's like a vaccine-associated adverse events. So one reason why we do it, what's the magic about the ontology? It's like you have the asserted one, you can have the inferred one. So the asserted one is like this, and the inferred one is like this, and sometimes it gives you more power. For example, in here we have live attenuated vaccines here, but in here is somewhere, so live attenuated vaccine is only itself. But by doing the inference, you can get all the vaccines under this category. So I think it's something many of you know. So it can give you additional power. Okay, so let's come to the I know. So the development of this one is like you want to competing with any other ontologies, right? It's because you don't find anything like yours. Well, you do find some partial things, and then you reuse the story. So for example, we are looking for interactions. And you will see, okay, gene ontology has a biological process. They have a lot of processes. So they can be considered as interactions. But they don't follow our definition, because our definition is an interaction is more like an arrow. You have a graph. You have one arrow. So you have an input, you have output. And they don't follow our definition. But they do have many things. You can use their definition, right? You can say, okay, they have some phosphorylation or another methylation. So you can use their things. You can import their things. So you don't have to, do the reinvent the wheel. You can reuse them. You can reuse the PCI, MI, and you can build up your own story. And then, as a whole, you have a good system. Doesn't bother you too much, but you can have your own interaction network built up. And you can also, this is new for us. So we have something called has visual mining keywords. So for this type of interaction type, often you don't know how to do visual mining to get this one. But you can rely on this. So each of these, as long as you can find any of the keywords, then you know it's one type of interaction. And you can do all these things for each level, right? Then in the end, so let's say I was talking about more than 800 keywords. So we assign the keywords to different levels. So once you do additional mining, then you have all the keywords. And by aligning to the ontology, then you know not only they are interacting, you also know the hierarchy of the interactions. So this is one example. So we use our system, we can find many over or down-regulated gene interactions just by using the I know structure, and we know what type of interactions we can find. So it's one benefit to use I know to look for the keyword pools and also to classify the interaction types, the hierarchy from the literature mined data. Well, this is my field one. Yeah, I know it's sometimes kind of my dream, but sometimes it goes too simple. But what I want to do is go from simple to high. So yeah, in a paper last year, I lay out. I say, okay, we have a theory. Definitely, we have a lot of back and forth with reviewers, some discussion. Eventually, they accept my paper. So the idea is like, okay, we have an elephant, 7 blind. So it's like an Indian legendary, right, story. So 7 blind people looking for what is the elephant looks like. So different people feel like a different way. So you touch the body, say, oh, elephant is a war. But of course, it's not a war. So I try to do the same. I try to see, okay, what happened about life? So I put together like 4 tenets. So the whole process of life of an organism is a single complex dynamic network. So we have the blueprint in the genome, and it starts at the moment when the first cell of organism forms, and the interaction between the genetic material and the environment can decide the phenotype. So I see the genetic material. So everything outside of the genetic material, outside DNA, can be considered as environment. So it can be intracellular and extracellular environment. So this is some story. I try to build up a whole system based on 4, and we consider add 1 more to basically represent the whole one net. But why you put it here? Why it's related to other things? Because I think we can use I know, as simple as I know, to as a foundation to build up a system to more like the knowledge base to form a huge ontology to include all the interactions as a blueprint, and the expression of the blueprint can be different form, given different conditions. So this is some story that I'm dreaming for. So so I want to compare my story with if you have the periodic table of chemical elements. So initially you invented just maybe 20 elements, but now you can use the form, you can predict new elements, right? So we can do the same thing. We can use ontology to build up a system to hold all the knowledge, and we can do prediction. This is kind of the dream thing. I think we can probably go. Okay, so let's see how. Okay, I think I still have some time. So let me go to the last section about the onto-animal tools. All tools are quite useful and have been used by many people. So we call it onto-animal tools. Onto-animal tools, and now people say, oh, then you have an onto tool. I say, okay, now we have onto tool. I put this one just last month. Yeah, we have onto tool, and this tool has many animals. Okay, so these tools can be used for different purposes. So each one is doing for only one thing. So the onto focus is the first one we developed, is to reuse existing ontology terms. So for example, I have the OAE, which has imported terms from over 20 other ontologies. And I have the I know, which imports terms from gene ontology, from the PSI, from many other ontologies. How do you do it? You don't want to do it manually. It takes forever, right? So you can use a tool to do it. And you can, so let's say if this is to get existing tools, what about you want to generate new terms, new ontologies? Because everyone knows ontology development can be very boring. So to make a breakthrough in ontology study, we need tools. It's more like you have a microscope, then you open a new area of microbiology. Well, I cannot compare with the other one. But the idea is like we need tools to advance the whole domain. Without it, if anyone is doing the manual generation, takes forever, the whole researcher won't go that far. So it motivates me to generate tools. So it's why our lab also generates many ontologies. So OntoRed can do the trick. So basically you can put all into the Excel kind of thing, and we can generate all the ontology terms for you just using your Excel file and some other patterns. And the He group RDF triple store now is the default RDF triple store for more than 90% of oval foundry ontologies. And we have OntoB for demonstration, for visualization, and this one is for comparison, and this one is for instance data analysis, and this one is also for community view. So I don't have a lot of time. I'm going to give you some quick demo on the 3 tools, the OntoFocus, OntoRed, and OntoB. So OntoB, the idea is like it serves as a link the ontology server for different ontologies, especially with the focus on on-board foundry ontologies. So we don't want to compete with the NCBO Bioportal, so we have a focus. And it starts when on-board foundry has a lot of terms. They will all put it in Bioportal, but they don't like Bioportal's way. They ask Bioportal all the time. And Bioportal said, no, we are not only for you, we are for all the others. So they didn't care. So eventually we developed one for various ontology, and they like it. And eventually, almost most ontologies in OBO default go to OntoB. So the default means like if you have a term like this one, for this adverse event, if you go to the web browser, you type the URL or URI, it comes to this page. So it means it's default page to demonstrate this information. So we can demonstrate the structure, the attributes, and the hierarchy. And as the linker data, you will stream like, okay, if I search for it, you will look for RDF, right? But for a web page, you look for HTML. So we did some magic thing. So when you look at it, it's like HTML, but if you click for the source page, you come to the RDF format. So the source page is RDF. You use Unicus, you do the some curl CURL, or you do some query the URL. What you get is this sort of page. But if you use the web browser, you get this one. And the display is quite nice. So most people just use this one. Some people are using this as well. And this feature is not available in Stanford Bioportal. Okay, what about the OntoFocus? This is just very simple classical demonstration. So this is the interface. So you can you can select an ontology. You can even search your term, and it will give you the hint. You can select. So you say you use the Homo sapien. What you want to do is like, oh, you know what? Because I don't want to get the whole hierarchy. So from the NCBI taxonomy ontology, from the Homo sapien to the eukaryota, there are 27 middle layers. For some people, they don't care. They just use. I just want to say, use Homo sapien, go directly to eukaryota. Yeah, the system can do it. You just do some different selection. You can do it. But some people like to have all the intermediate terms. Yeah, we can do it easily. Just literally just these few lines, or you can put a few things here. We get all the information for you. And yeah, you can open in our editor, and you can visualize it. So it's something like, if you want to get a lot of terms from other ontologies, you just give minimal information. You say, okay, I want to get a term, I want to how it's organized. And then we just do it. Even you don't have to use a browser, you can just use a program to run it. We get all the information, then you import the subset of ontology into your own ontology. That's it. It does all the trick. So many people like the story. So what about I want to not just using existing terms, I want to generate new terms. We do the same thing. We have something called OntoRed. So it's based on the so-called ontology design pattern, so ODP. So you have an ontology design pattern. So let's say we have a pattern like this one. So you can build up your Excel file. So each column, the header of each column is mapped to the node, right? And the relation between all these can be formed by putting some more like you use Manchester format in project. You can put some relation there. You may use some variable, but then you just click. In the end, after you have the setting, you have the file, you click, you say I want to do it. So it can generate all the terms for you, and you put it into your ontology. So quickly you have all the work done. So what you need to do is to have an Excel file and have a pattern, and then you program the pattern using the simple Manchester format. You put it there, and what you get is ontology. So it's a very simple way, and this tool was published last year, and more and more people are using it now. So basically, I want to summarize today's talk. So I have demonstrated to you that the OAE can classify different ontologies different adverse event terms. So it's not as knowledge based. It's more like a classification of terminologies, but it's quite useful as I showed you. It's more advanced than the measure, the default one. And I showed you the OVA, AE, and the OD, NAE can function as knowledge base because it summarizes all the data from what we know, and by linking to different ontology structures and knowledge, and now we can actually query the ontology and get more insights from just the querying. And I showed you the INO can classify intention terms and support literature mining, and can even be used as some platform for my doing the OneNet theory study. And then I showed you the Ontology tools can support ontology visualization, reuse, and development. So the question is, what's next? So we have a lot to do, and the tools can be used by many, and we are getting a lot of requests, and we are still improving our tools and the ontologies. This tool is more like a complete. We can add more features, and as I know, it's the beginning. We are adding more things into there, and the OAE has 4,000 terms, but the VAERS and the FAERS, they usually use like 5,000 to 7,000 major terms. So we still need to do more work in order to get more terms in, so we can use OAE better for analysis of different use cases. So yeah, so this is my acknowledgement. So most work was done previous years, which was funded by the R01 grant, and we have many collaborations. Thank you.
Two questions. Okay. Number one, ontology is the foundation of web simulation. It's very important, very useful, but it's hard to show the reliability and validity. How do you justify this ontology is real? It's true. Okay. You can do that in many different ways. So I just want to hear about your opinion on how to do this. The second one is that ontology, generative ontology is very time sensitive. Okay. And one potential way to do it is to automate the process through machine learning, whatever. Doing this by hand is good for now, but in the future maybe that's cannot be sustained. So I just want to hear your idea about how to potentially move the ontology generation, validation into a more machine-based automatic process.
So yeah, just two wonderful questions, and people are talking about this all the time. And so my addressing your first question is like this. So yes, there are different ways to develop ontologies. So the way that I'm using, that I would recommend everyone to use, although you probably can disagree, is to follow a standard rule, like we use Open Foundry. So you follow the standards, and you follow the leader. If you have an upper level ontology, so we use Buffer. Doesn't mean Buffer is perfect. Buffer still have issues. And if you do the following the Buffer, if the top level ontology makes some small change, you may have to change a lot. So still have issues. But long term, it's wonderful to follow it because everyone is following it, and all the ontologies can be interchangeable. So like we have developed many ontologies. We all follow Buffer. So you can literally merge everything together very easily. It becomes a huge ontology. So you can do it quite easily. And so there are different ways to do it. And so I'm collaborating with another, like a Mayo Clinical investigator, so they are not using it. So sometimes they have different ways to do it. I said, okay, let's follow the traditional, my kind of oval way. And then we have more restriction. Oh, you have to do this way. So we think it's better. In terms of how to verify your ontology, so in our study, we really follow the use case applications. So all the ontology development we have, we basically verified based on use cases. So you can demonstrate, okay, I developed I follow the kind of convention standard, and I can use it. I can show you, okay, each ontology has rationale, why we do it, how we do it, and then we can demonstrate by follow it, and we can do, you can also do some reasoning, make sure there's no error from the reasoning. So there are different ways to verify it, to do a good job, and to make it useful. So in terms of the second question, so yeah, so developing ontology is very time consuming. So nowadays, also ontology development is a very kind of booming business. A lot of people are doing it, so the quality may not be that good equally, and doing it is time consuming. How you compare it is time consuming. So as I briefly mentioned, I think the key to the problem is the software. And also, as you said, like the relational mining, the NLP can help come to a lot of things quickly. There may be outsourcing, like crowdsourcing. So instead of, because nowadays ontology development is more small group driven one. But what about, let's say if we have, actually we are doing some prototyping now. If we develop ontology, we put it all into more like a wiki kind of a thing. We let people to vote, to change. So slowly it will become better and better. And then, because all the community are contributing, eventually you can probably quickly come to some very solid ontology. You will never say it's perfect, but it's like a wiki. The information is, the quality of Wikipedia is improving every day. So I think some strategy like that one can be used. So how to get more community involvement and how to develop better tools is are the two keys that the ontology field can go further. And once we have good ontologies, all the applications can rely on ontology. And then I think we are going to have a better future on biomedical informatics. As you acknowledge it, ontology is the foundation, and I truly believe it. If we can do a good job, and we will be in a better position for different applications.
So I'm going to make an intentionally provocative statement, and you can, and I would love to hear that I'm totally wrong.
Okay.
And I would love to hear examples of how I'm wrong. So there are thousands of ontologies. There's been, if we even say from Mark Muson's Ph.D. Onward, there have been hundreds, if not thousands, of people working on it. There are dozens, if not more, tools. And there are ontologies of all sorts for every conceivable area. Other than information retrieval, specifically mesh, and perhaps you could argue the UMLS, are there ontologies in widespread clinical use?
Yeah, that's a good question. So I agree, there are hundreds of ontologies. So about 10 years ago, many people are looking for the biomedical investigations, right? So you have the Miami minimal information for microarray. So they are developing their ontology for microarray study. And there is an imaging group. They are developing their ontology for imaging. There is an immunology group. And there are many groups. And they are all developing their own ontologies.
Do you mean DICOM?
Huh?
Do you mean DICOM?
DICOM? Well, yes. Yeah,
I mean, I think of that as a standard. I mean, you can certainly imagine.
You can imagine many more.
Well,
yeah.
no. You can imagine. It may be unfair to exclude DICOM. So.
Yeah, I agree. So in the end, they said, wait a minute. So they met in meetings. They said, oh, I'm looking with. Hey, I'm also looking. Oh, they said, wait a minute. Why not we work together instead of looking at differently? Because we are all working on biomedical investigations. So this is why the so-called ontology of biomedical investigation, so it's called OB, came from. So I'm the representative of the vaccine or vaccination domain in OB. So we have more than 20 communities working together on OB. So OB now is one of the highly cited ontologies. So yeah, this is an example, I think, and it's the way we should go. So we should all work together and work on toward the same goal. And we should all have the ontologies which can be interchangeable interoperable, we should adopt an upper level ontology. I'm not saying buffer is perfect. You know, you can say, okay, I don't use buffer, I don't like it. Yeah, let's use another one. But you think in 50 years, in 100 years, there must be buffer, something like a buffer or some other ontology which stands out as an upper level one. It covers all the fields and all the different ontologies that stay together to form a huge one. It becomes more like a language for machine learning, a language. So if we talk about it in English, right? If we talk in France or in China, Chinese, we don't agree with each other. But if we all talk about English, we agree with each other. We know, we understand each other. So if eventually we have something like a OBO kind of thing, OBO now has more than 100 ontologies. If eventually we come to a way it's non-redundant certain, and it becomes an English for us to talk, and becomes a certain for computers to communicate. And I think that's more like one ultimate goal so that we are working on ontology development.
No, I totally agree about the promise, and I agree about the kind of the goals. No argument. I guess I'm just one way of putting it is, what's your assessment of impact to date?
Impact? I think that the impact is
Of the entire field.
entire field is growing very well. Yeah, well, you know, I'm
Perhaps
working
the
on it.
reason we're in the problems we are is because we're not using the ontology.
No,
And there's a negative proof.
well, but I guess what I'm asking is, why aren't we using it? So,
Because of people like you.
people like
It's doctors that are problem, not the informaticians. We understand the importance of an ontology.
Now I understand. The 1990s are the answer.
We're coming back.
Yeah.
It's like enrollment ontology that's being used now.
I'm sorry?
The enrollment thing that Jihad they implemented.
Oh, you mean consent?
Consent
Yeah, I mean, there are hundreds. I haven't counted the ontologies. There are lots.
Lots.
But
And
they are
there's
using.
somebody using it, something somewhere.
Yeah.
And kind of overall, and I guess I was just asking for a comment on that.
Yeah.
Well, I think the other point is that SNOMED apparently is not an ontology, or ICD-9. So we tried.
Right.
We use those all the time. We just
Right.
didn't pick a good one.
Right.
We're going to pick the bad one.
Okay.
I wanted
Some
to
people
get
are
back to
stupid,
your
some
work. I
are
wanted to
not.
hear a little more understanding on the genotypes tied to the adverse events, the number of genes tied to the events. How is that really done? Because when you go to like the FDA to do an adverse event, you don't know the genetic profile of the patient. How are you connecting the genetic profile to determine the associations to the adverse events? Is it just a limited group of cancer patients that you're working with, or how is that really done?
That's a good question. So this is how I vision. I think that there's nothing like this, a perfect solution yet. So my vision is like, you know, based on what we know from our studies, our literature, we can possibly build something like ontology that can collect all the knowledge, all the information we have to point, okay, we have the SNP, we have the changes, and it has the phenotype, right? So if we can have a huge database or huge knowledge base that it has all the information, so you consider it more like our blueprint thing. So for any specific patient or somebody, so we can do the sequencing or anything. Then if we can identify some SNP changes, then we can query the knowledge base. We say, oh yeah, you do have the change, the genetic variation. So the likelihood of this one linking to some adverse event or some phenotype or some other things may have already somehow represented in the ontology, or if not represented in ontology, you can develop an additional statistical tools or some tools that are working together with ontology can give you the answer. So I think that this is something, you know, hopefully.
It seems like right now the proposal for the precision medicine program in the United States is to collect genetic information on 1 million patients. But to be able to use that, it sounds like that ontology will need to be present to be able to analyze that information back to clinical outcomes and adverse events.
Yeah.
Smart guy in the back.
Huh?
Yeah.
that's what's gonna be necessary?
Yeah, when the doctor's gonna start doing that?
Yeah, I'm off to do that right now.
Oh. We'll see you next week.
I do it wrong, but I'm doing it sure.
Yeah, the clinical one, yeah, definitely has a lot to do, and probably is relatively weak in ontology development in terms of the clinical